Look at your hands for a second. Those fingers, the skin, the blood flowing beneath the surface, every single part of you is built from something astonishingly small, something invisible to the naked eye. Atoms, these microscopic building blocks, are the reason you exist, the reason trees grow, the reason stars burn in the night sky. And here's something that might blow your mind. The atoms in your body right now were forged inside ancient stars billions of years ago. You are literally made of stardust. So how did these tiny particles become the foundation of everything? Why does the universe rely on them to construct planets, oceans, and even consciousness itself? Think about the last time you took a breath, that air filling your lungs, a swirling dance of atoms, the screen you're staring at right now, a carefully arranged lattice of them. From the phone in your hand to the farthest galaxy we've ever observed, atoms are the universal language of matter. But here's the wild part: despite being everywhere, atoms are mostly empty space. If you could zoom in close enough, you'd find a nucleus smaller than a pinhead, with electrons whizzing around it at unimaginable speeds, all separated by vast distances. So why does something so seemingly fragile and sparse feel solid to us? How does nothingness come together to create everything we know? This isn't just a story about science, it's a story about connection. The same atoms that make up your bones once floated through supernova, drifted across cosmic clouds, and found their way into the soil that grows your food. They've been part of dinosaurs, part of mountains, part of countless lives before yours. And today, we're going to unravel their secrets. We'll travel back to the birth of the universe to see how atoms first came to be, explore why they're the perfect building blocks for reality, and discover what their existence tells us about our place in the cosmos. By the time we're done, you'll never look at the world or yourself the same way again. So let's begin. The universe began not with atoms, but with pure energy, an unimaginable fireball of heat and light. In the first trillionth of a second after the Big Bang, conditions were so extreme that even the simplest particles couldn't hold together. But as the cosmos expanded and cooled, something remarkable happened. Quarks, those elusive fundamental particles, finally had a chance to stick together, forming protons and neutrons. Electrons, too, began to emerge from the chaos. Yet for nearly 400,000 years, the universe remained too hot for these particles to settle down and build anything stable. It was like trying to assemble a sandcastle in the middle of a hurricane. Then came the cosmic moment that changed everything: a drop in temperature just enough for electrons to be captured by atomic nuclei, creating the first true atoms. Picture this: a universe filled with nothing but hydrogen and helium, the simplest atoms possible. No planets, no stars, just a vast, glowing fog of these primordial elements. But within that simplicity lay the seeds of everything to come. Hydrogen, with its single proton and electron, became the universal raw material. Gravity would later pull these atoms together into stars, where the real magic of atom building began. Here's what's truly mind-bending: every atom heavier than helium, the carbon in your cells, the oxygen you breathe, the iron in your blood, was forged in the hearts of stars. When those first stars ignited, their crushing pressures and searing temperatures fused hydrogen and helium into heavier elements. And when massive stars died in spectacular supernova explosions, they scattered these new atoms across the cosmos like cosmic gardeners planting seeds for future worlds. That means the calcium in your bones, the gold in jewelry, even the silicon in your phone, all of it was cooked up inside stars that lived and died before our solar system even existed. This cosmic recycling explains why atoms are so universal. They're not just building blocks, they're survivors, carrying the history of the universe within them. The hydrogen in your body's water molecules might be 13.8 billion years old, unchanged since the first minutes of creation. Other atoms, like the iodine in your thyroid or the zinc in your enzymes, were likely born in multiple generations of stars, each explosion enriching the galaxy with new possibilities. So when we say everything is made of atoms, we're really saying everything is stitched together from the universe's own memory, a living archive written in particles. At first glance, an atom might look like a miniature solar system, a dense nucleus at the center with electrons whirling around it. But this familiar image hides something far more extraordinary. That nucleus, made of protons and neutrons, contains nearly all an atom's mass, squeezed into a space so tiny it defies comprehension. If you expanded an atom to the size of a football stadium, the nucleus would be no bigger than a single grain of sand on the 50-yard line. Yet despite its minuscule size, the nucleus holds the atom together with an iron grip, thanks to one of nature's strongest forces, the aptly named strong nuclear force. Without it, every atom in the universe would fly apart in an instant. Now, let's talk about those orbiting electrons. They're not just tiny planets following predictable paths. They exist in a kind of quantum cloud, buzzing around the nucleus in specific energy levels. Think of it like a beehive where bees don't move in neat circles but appear everywhere at once within their designated zones. This behavior is why atoms can bond with each other in the first place. When two atoms get close enough, their electron clouds overlap, creating a sort of shared territory. Sometimes electrons are traded, sometimes they're shared equally, but either way, it's this dance of electrons that builds molecules from the water in your glass to the DNA in your cells. Here's where the magic of atomic design really shines. Protons give an atom its identity, change the number of protons, and you've got an entirely different element. Add one proton to hydrogen and suddenly it's helium. Add 6 more and now it's oxygen, the element that keeps you alive. Neutrons, on the other hand, act like atomic glue, stabilizing the nucleus. Too many or too few, and the atom becomes unstable, leading to radioactive decay. It's this precise balancing act, protons defining an element, neutrons keeping it intact, and electrons dictating how it interacts, that makes atoms the ultimate Lego bricks of reality. And just like Lego, the way atoms connect determines what they build. Take carbon, for example. With its 4 available bonding spots, it can form long chains, intricate rings, or even hollow spheres, giving us everything from the graphite in pencils to the diamonds on engagement rings. Oxygen, with its 2 open slots, loves to pair up, creating the O2 molecules we breathe. But mix carbon and oxygen in the right arrangement, and you get carbon dioxide, a gas that plants crave. The same few types of atoms, rearranged, produce substances as different as soft rubber and hard steel. This versatility explains why atoms dominate the universe's construction plans. They're not just simple or random, they're perfectly tuned to create complexity. The nucleus provides stability, electrons enable endless combinations, and the empty space inside atoms, yes, the same emptiness we mentioned earlier, allows for flexibility. If atoms were solid little marbles, they'd just clump together uselessly. Instead, their mostly empty interiors let them shift, bond, and reorganize, paving the way for galaxies, giraffes, and everything in between. So the next time you pick up an object, remember, you're holding a masterpiece of atomic engineering, a testament to how simplicity at the smallest scale gives rise to all the richness of our world. If atoms are the alphabet of the universe, then the periodic table is the dictionary, a master list of every possible element nature can create. Each box on that chart represents a unique atomic recipe defined by one crucial number, the count of protons in its nucleus. Take hydrogen, the simplest atom with just one proton. It's the fuel of stars, the backbone of water, and the most abundant element in existence. Add one more proton, and suddenly you've got helium, the lightweight gas that fills birthday balloons and keeps stars burning steadily. But the real wonder begins when atoms grow more complex. Carbon, with its 6 protons, becomes the scaffolding of life, while oxygen's 8 protons make it the breath of every animal on Earth. This proton count isn't just trivia, it's the ultimate cosmic ID card. Change the number and you change everything about how an atom behaves. Iron, with 26 protons, anchors your blood cells and forms the cores of planets. Gold, with 79, resists corrosion and conducts electricity so well it's woven into astronaut helmets. And uranium, with 92, packs enough energy to power cities or devastate them. The periodic table isn't just a grid. It's a story of how tiny variations in atomic architecture create substances as different as neon lights and the calcium in your teeth. What's astonishing is how few ingredients it takes to build reality. Just 4 elements, hydrogen, oxygen, carbon, and nitrogen, make up 96% of your body. The same carbon that's in your pencil lead is the foundation of every protein in your cells. The oxygen you exhale is the same gas that rusts metal and fuels forest fires. This versatility comes from how atoms share electrons, forming bonds as flexible as a handshake or as unbreakable as a diamond's grip. Silicon, right below carbon on the periodic table, can't create life like its sibling, but it's perfect for crafting computer chips that run the modern world. Periodic table also reveals a hidden rhythm. Elements aren't randomly placed, they're grouped by shared traits. The far right column holds the noble gases helium, neon, argon, content to stay solitary, rarely reacting with others. On the left, alkali metals like sodium and potassium explode in water, desperate to donate electrons. This predictability lets scientists dream up new materials before they're even made, from superconductors to alloys stronger than steel. Even the gaps in the table tell a story. Elements like technetium, with 43 protons, don't exist naturally on Earth because their atomic structures are too unstable. They're forged in labs or dying stars. Here's the profound truth hidden in those squares. Every element, from lithium to lawrencium, was either born in the Big Bang or forged in stellar furnaces. The gold in your jewelry likely came from colliding neutron stars. The iodine in your salt traces back to supernova that rained it down on young planets. And the rare earth metals in your smartphone, they're remnants of ancient cosmic alchemy, concentrated over eons by geological chance. The periodic table isn't just a tool for chemists, it's a family tree of stardust, showing how the universe recycles its building blocks across time and space. This atomic diversity explains why we don't live in a monotonous universe of just hydrogen and helium. Without heavier elements, there'd be no rocky planets, no oceans, no DNA. Titanium couldn't strengthen jet engines, and copper couldn't carry electricity. The fact that atoms can arrange themselves into 94 naturally occurring elements, and even more synthetic ones, is why reality has texture, color, and function. From the sulfur that makes volcanoes smell to the phosphorus that powers your cells, each element plays a role in the grand atomic symphony, and the wildest part. Every one of them, no matter how rare or exotic, follows the same simple rule. Change the proton count, and you change the story of matter itself. Consider the life cycle of a single atom of oxygen floating in space right now. Its journey began billions of years ago inside a massive star, where temperatures exceeded millions of degrees, smashing together lighter elements to forge something new. When that star eventually ran out of fuel, it didn't just fade away. It went out in a blaze of glory, erupting in a supernova so powerful it could outshine an entire galaxy. In that cataclysmic explosion, our oxygen atom was hurled across light years, joining a swirling cloud of cosmic debris. Over eons, gravity pulled that cloud together, forming new stars, rocky planets, and eventually the air you're breathing at this very moment. This recycling process isn't just poetic, it's the universe's most efficient supply chain. Every time a star dies, it enriches the cosmos with heavier elements, the very ingredients needed for planets to form and life to emerge. Take Earth's iron core, for example. Those atoms were likely forged in multiple generations of stars, some so ancient they burned out before our solar system even existed. The gold in your jewelry, that probably came from two neutron stars colliding, sending ripples of precious metals through space. Even the silicon in the sand beneath your feet was once part of a red giant star's fiery outer layers. What's truly humbling is how sparse these heavy elements are. Despite their importance, atoms heavier than helium make up less than 2% of the visible universe. Hydrogen still dominates just as it did in the beginning, yet that tiny fraction of carbon, nitrogen, and oxygen is what makes all the difference. Without them, planets would never solidify, water couldn't exist, and complex molecules like DNA would be impossible. It's as if the universe spent billions of years carefully stockpiling rare ingredients, waiting for the perfect conditions to mix them together, and mix them it did. In the dusty rings around young stars, atoms collided and stuck together, forming ice, rock, and organic compounds. Some of those specks became comets, which later bombarded early Earth, delivering water and possibly even the building blocks of life. Others gathered into asteroids, preserving pristine samples of the solar system's original material. Even today, telescopes spot complex molecules like ethanol and formaldehyde floating in interstellar space, proof that atoms don't just create matter, they set the stage for chemistry on a cosmic scale. This explains why astronomers get so excited about finding exoplanets in the Goldilocks zone, regions where temperatures allow liquid water. Water, after all, is hydrogen and oxygen in perfect partnership, a molecule so versatile it can dissolve salts, float ice, and cradle living cells. The fact that it exists at all is a testament to atoms' ability to combine in precise, life-friendly ways. And since hydrogen is everywhere and oxygen is common in star debris, water might be far more abundant in the universe than we once thought. But atoms don't just build worlds, they also destroy them. When a massive star collapses into a black hole, its atoms are crushed out of existence, their protons and neutrons ripped apart. In the accretion disks around these cosmic monsters, atoms are accelerated to near light speed, glowing fiercely with X-rays. Even in death, they transform into something new, feeding quasars that can outshine 1,000 galaxies. It's a reminder that atoms are more than just static building blocks. They're dynamic participants in the universe's grand story, constantly changing form but never truly disappearing. So the next time you feel insignificant under the night sky, remember this: you're breathing star fragments, walking on ancient stellar wreckage, and thinking with atoms that have witnessed the birth and death of suns. The cosmos isn't some distant, untouchable realm. It's in your bones, your blood, every beat of your heart. And out there, right now, new atoms are being forged in stellar furnaces, destined one day to become part of worlds and lives we can't yet imagine. The universe writes its history in atoms, and we, like every planet, every star, are its living, breathing sentences. atoms seem almost too perfect, like nature's cheat code for building reality. But why them? Why not some other arrangement of particles? Imagine if the universe had picked a different set of rules, where protons were slightly heavier or the strong nuclear force a bit weaker. Suddenly, atoms wouldn't hold together and complexity would crumble before it even began. The fact that atoms exist at all is a razor's edge miracle, dependent on precise balances between forces most of us never think about. Take the proton, for example. It's just stable enough to last for billions of years, yet not so rigid that it can't participate in cosmic change. If protons decayed faster, like some theoretical particles do, stars wouldn't have time to form, let alone create heavier elements. On the flip side, if the electromagnetic force was stronger, electrons would cling too tightly to nuclei, preventing atoms from ever sharing electrons to form molecules. It's this Goldilocks stability that makes atoms the universe's go-to architects. Compare them to muons, those heavy cousins of electrons that pop up in particle accelerators. Muons behave like electrons but vanish in microseconds, far too fleeting to build anything lasting. Or consider quarks, which can't even exist alone in nature. They are always bound together inside protons and neutrons. Atoms work because they're the sweet spot between permanence and flexibility, durable enough to endure eons but adaptable enough to create everything from water to DNA. Then there's the puzzle of antimatter. For every particle, there's an antimatter twin with opposite charge. When matter and antimatter meet, they annihilate in a flash of energy. If the early universe had been perfectly balanced between the two, all atoms would have vanished in a cosmic fireworks show. But somehow, matter outnumbered antimatter by 1 in a billion, just enough to leave behind the building blocks we see today. Without that tiny asymmetry, there'd be no stars, no planets, just an empty void. Even the emptiness inside atoms plays a role. If subatomic particles were packed tightly like marbles in a jar, matter would be unimaginably dense. A sugar cube's worth of neutron star material weighs as much as a mountain, and that's what all matter would resemble without atomic spaciousness. But because atoms are mostly void, they can overlap, interact, and bond without collapsing into cosmic sludge. It's this delicate interplay of presence and absence that lets chemistry happen at all. So when we ask why atoms rule the universe, we're really asking why the laws of physics allow complexity to exist. The answer isn't just about atoms themselves, it's about the forces that sculpt them, the energies that sustain them, and the cosmic accidents that preserved them. In another universe with different constants, atoms might be impossible, and reality could be a featureless sea of particles that never quite connect. But here, in this universe, atoms are the quiet geniuses of existence, turning chaos into galaxies, cells, and the very thoughts you're having right now. Zoom in close enough, and the familiar world of atoms dissolves into something far stranger, a realm where particles don't behave like tiny billiard balls but as ghostly waves of possibility. This is quantum mechanics, the rulebook for the subatomic world, and it defies every instinct we've developed living in a world of tables, trees, and tangible objects. Take an electron, for example. It doesn't orbit an atom's nucleus the way Earth circles the Sun. Instead, it exists as a probability cloud, a sort of blurred smear where the electron might be, vanishing and reappearing in different locations without ever taking a clear path between them. It's as if you tossed a ball in the air and it momentarily became a fog of potential positions, only to snap back into solidity when you blinked. This quantum fuzziness isn't just theoretical quirkiness, it's the secret sauce that makes chemistry work. When two atoms approach each other, their electron clouds don't collide like bumper cars. They overlap and merge, creating shared zones where electrons act as a glue. Imagine two soap bubbles touching and forming a bridge between them. That's how atoms bond, thanks to electrons being in multiple places at once. Without this behavior, water wouldn't flow, DNA couldn't twist, and the thousands of chemical reactions keeping you alive every second would grind to a halt. Then there's quantum tunneling, perhaps the most mind-bending trick in nature's playbook. Particles can literally vanish on one side of an energy barrier and reappear on the other, as if teleporting through walls. In the sun's core, hydrogen nuclei fuse into helium because protons tunnel through barriers that should, by all classical laws, keep them apart. Without this effect, stars wouldn't shine, and the universe would be a dark, lifeless void. Even your own cells rely on tunneling enzymes. Use it to speed up reactions that would otherwise take centuries, letting you digest food and think thoughts in real time. What's wild is that these quantum shenanigans don't add chaos to the atomic world, they add precision. Electrons occupy specific energy levels like rungs on an invisible ladder, and they can't exist between those steps. This quantized structure is why atoms of a given element always absorb and emit light at the exact same wavelengths, creating the unique spectral fingerprints astronomers use to identify elements across the galaxy. It's also why materials have distinct colors. Gold isn't yellow because of some arbitrary paint job. Its electrons interact with light in a way that's dictated by quantum rules, reflecting just certain shades while absorbing others. Even the stability of matter itself hinges on quantum quirks. If electrons were classical particles, they'd spiral into the nucleus in a fraction of a second, collapsing every atom in the universe. But thanks to a quantum principle called the exclusion rule, no two electrons can occupy the same state at once. This creates an invisible scaffolding that keeps atoms puffed up and solid, like an unstoppable force field. It's why you don't fall through your chair despite both you and it being overwhelmingly empty space. The solidity you experience is really just a quantum illusion, a trillion tiny repulsions happening every nanosecond. So while quantum mechanics might seem like an abstract theory reserved for physicists in lab coats, it's actually the silent choreographer of everyday reality. The screen you're staring at, its LEDs rely on quantum dots to produce vivid colors. The GPS in your phone, it corrects for time dilation effects predicted by quantum field theory. Even the photosynthesis fueling every leaf outside depends on quantum coherence, where particles explore multiple energy pathways simultaneously to find the most efficient route. Atoms work because quantum mechanics lets them dance on the edge of impossibility, balancing uncertainty with exquisite order, randomness with perfect reliability. And that's the ultimate irony. The universe's most fundamental layer, the one that seems the most alien to our experience, is the very reason anything exists at all. Carbon is the universe's ultimate multitasker, an element so versatile it can form long chains, intricate rings, and even hollow cages, all thanks to its 4 bonding hands. Picture a molecular playground where carbon atoms link up like Lego bricks, creating structures as simple as methane or as complex as the 30,000 genes in your DNA. This isn't just chemistry, it's cosmic craftsmanship. While silicon sits right below carbon on the periodic table and can technically form similar bonds, it's like comparing a Swiss Army knife to a rusty spoon. Carbon's bonds are strong enough to hold together but flexible enough to break and rearrange, making it the only element capable of building the millions of molecules life requires. Now imagine the first spark of life on Earth, a warm tide pool under a young sun, where carbon atoms floated in a soupy mix of water and minerals, some of them hooked up with nitrogen, oxygen, and hydrogen, forming amino acids, the alphabet letters of proteins. Others strung together into sugars and phosphates, the backbone of genetic code. What made these carbon compounds special wasn't just their structure, it was their ability to store information. A single DNA molecule packs more data than a supercomputer's hard drive, all written in sequences of carbon-based nucleotides. And here's the kicker: those same coding molecules exist in every organism from bacteria to blue whales, proof that carbon's language is universal. But life doesn't just use carbon, it recycles it relentlessly. The carbon dioxide you exhale might become part of a leaf tomorrow, then a carrot next month, and eventually someone else's muscle tissue. This endless loop, called the carbon cycle, connects every living thing on Earth. Even fossil fuels are just ancient sunlight trapped in carbon bonds, formed when prehistoric plants compressed over millennia. It's no exaggeration to say carbon is the ink in life's pen, writing and rewriting its story across eons. And yet, carbon's brilliance isn't solitary. It teams up with other atomic all-stars to pull off life's miracles. Oxygen, for instance, acts like a molecular battery. Carbon hands it energy packets in the form of glucose, and mitochondria cash them in to power your cells. Nitrogen, scooped up by soil bacteria, becomes the backbone of amino acids. Even trace elements like iron and zinc hitch rides on carbon frameworks, turning enzymes into microscopic factories. This collaborative dance of atoms is why a human body isn't just a bag of chemicals, it's a symphony of atomic partnerships, each player vital to the score. What's haunting is how close we came to a carbon-less existence. If the strong nuclear force were even slightly weaker, carbon atoms wouldn't form in stars at all. In the 1950s, physicist Fred Hoyle predicted a specific carbon energy level later confirmed that allows stars to forge it efficiently. Without that precise nuclear resonance, the universe might be full of stars and planets but devoid of trees, tardigrades, or thinkers. Carbon isn't just lucky, it's inevitable in a universe fine-tuned for complexity. This brings us to a humbling truth: the atoms in your eyelash, your coffee cup, and the atmosphere overhead aren't just sitting there. They're engaged in a quadrillion chemical conversations every second, trading electrons, sharing orbits, and rebuilding themselves into new forms. Life isn't something that happens to atoms, it's something they do, a behavior as natural as hydrogen fusing in a star. When you bite into an apple, you're not just eating fruit, you're borrowing carbon atoms that might have once been part of a dinosaur's tooth, a comet's tail, or a fern in a prehistoric swamp. The universe could have been a silent museum of rocks and gas. Instead, thanks to atoms like carbon, it's a living, breathing story, and we're its latest sentences. Electrons are the ultimate social butterflies of the atomic world, constantly on the move, forming connections and reshaping matter with their restless energy. While protons define an atom's identity, it's the electrons that determine how that atom behaves, interacts, and ultimately builds the world around us. Picture them as tiny negotiators, shuttling between atoms like cosmic diplomats forging treaties. When sodium meets chlorine, for example, it's an electron that jumps ship, transforming a deadly metal and a toxic gas into harmless table salt. This single exchange illustrates the invisible power electrons wield, turning raw elements into substances we can touch, taste, and even rely on to survive. What makes electrons so extraordinary is their dual nature. They're not just particles, they behave like waves too, existing in fuzzy clouds of probability around the nucleus. These clouds aren't random, they're organized into specific energy levels, like floors in a skyscraper where electrons can only occupy certain apartments. The outermost electrons, called valence electrons, are the ones that matter most. They're the free agents, the ones willing to switch teams, and their availability dictates whether an atom will be a loner like neon or a social connector like oxygen. Consider water, the molecule that makes life possible. Its magic lies in how electrons are shared between one oxygen atom and two hydrogens. Oxygen, with its 6 valence electrons, greedily hoards them closer to its nucleus, creating a slight negative charge. The hydrogens, left with a more positive tilt, end up forming weak bonds with other water molecules. These hydrogen bonds, powered entirely by electron behavior, give water its surface tension, its ability to dissolve salts, and even its strange habit of expanding when frozen. Without electrons orchestrating these subtle attractions, lakes would freeze solid from the bottom up, and your cells would collapse like deflated balloons. DNA takes electron teamwork to another level. Its iconic double helix is held together by electrons shared between nitrogen, carbon, and oxygen atoms, partnerships so precise they can copy themselves with near-perfect accuracy. When cells divide, it's electrons that unzip the DNA ladder and electrons that help stitch together new strands. Even mutations, the raw material of evolution, often come from electrons getting bumped into the wrong places by radiation or chemicals. These microscopic missteps, multiplied over billions of years, gave us everything from ferns to human consciousness. Metals showcase electrons' versatility in a completely different way. In a copper wire, the outermost electrons don't belong to any single atom. They form a chaotic sea, flowing freely between nuclei. This electron mobility is why metals conduct electricity so well. Apply a voltage, and that electron sea surges in one direction like a school of fish. Gold takes this a step further. Its electrons vibrate in sync with light waves, reflecting certain frequencies to create that iconic gleam. The same principle explains why mercury is liquid at room temperature. Its electrons resist locking into rigid bonds, keeping the metal slippery and unpredictable. Perhaps most astonishing is how electrons enable vision. When light hits your retina, it's absorbed by molecules called opsins, where photons knock electrons into higher energy states. This tiny jump triggers a cascade of signals your brain interprets as color. The red of an apple, the blue of the sky, they are all stories told by electrons interacting with light. Even fireflies harness electron energy, exciting molecules to release light with nearly 100% efficiency, putting human light bulbs to shame. This invisible choreography extends beyond Earth. Auroras dance when solar wind electrons spiral down magnetic field lines, smashing into atmospheric atoms. Stars glow because electrons in hydrogen atoms leap between energy levels, releasing photons. The entire universe communicates through electron transitions, every nebula's color, every planet's composition, even the spectroscopic signatures astronomers use to hunt alien worlds. Electrons aren't just participants in chemistry. They're the universe's way of building complexity from simplicity, one atomic handshake at a time. Yet for all their importance, electrons remain elusive. They can't be pinned down to a single location or path. Heisenberg's uncertainty principle forbids it. Trying to observe them directly is like mapping a tornado by tossing confetti into it. This inherent fuzziness isn't a bug. It's the feature that allows electrons to form bonds, tunnel through barriers, and enable the quantum weirdness that makes reality possible. So while we often picture atoms as miniature solar systems, that image falls apart at the quantum level. The truth is far stranger, a buzzing hive of probabilities where electrons exist everywhere and nowhere until the moment they're needed. The next time you feel a static shock or watch a sunset, remember, you're witnessing electrons in action, the unsung architects of everything from salt crystals to symphonies. They prove that the universe's most powerful forces aren't always the most obvious. Sometimes they're the tiny, restless particles dancing in the empty spaces between what we call solid matter, stitching the cosmos together one bond at a time. Every swipe of your smartphone screen, every click of a mouse, every flicker of a light bulb, these everyday miracles are powered by humanity's mastery of atomic manipulation. Take silicon, the unsung hero of the digital age. A single grain of sand, purified and precisely doped with atoms like phosphorus or boron, becomes the foundation of microchips that process billions of calculations per second. It's the atomic imperfections, those carefully introduced foreign atoms, that allow silicon to switch between insulating and conducting states, creating the binary language of ones and zeros that underpins everything from text messages to space telescopes. Batteries tell an even more electrifying atomic story. Inside a lithium-ion battery, atoms of lithium shuttle between electrodes like microscopic couriers, carrying charge with each movement. What makes lithium special isn't just its lightness, it's how eagerly its outermost electron jumps ship, creating the current that powers your laptop or electric car. Cobalt and nickel atoms in the cathode act like atomic parking garages, storing lithium ions until they're needed. This delicate dance, perfected over decades of research, demonstrates how tweaking atomic arrangements can revolutionize energy storage, from the first lead-acid batteries to tomorrow's solid-state designs that might triple capacity. Then there are rare earth elements, the shadow architects of modern tech. Neodymium atoms, aligned just right in magnets, generate fields strong enough to spin wind turbines or vibrate your phone silently. Europium and terbium, sprinkled into screens, emit precise shades of red and green that bring pixels to life. These elements aren't actually rare, they're just notoriously difficult to separate from their ores, requiring atomic-level precision to isolate. A single iPhone contains over half the periodic table, with gold-coating circuit board contacts, tantalum in capacitors, and even trace amounts of yttrium in the camera lens. What's revolutionary is how we've moved from using atoms passively like iron in ancient tools to actively engineering their behavior. Graphene, a sheet of carbon just one atom thick, conducts electricity better than copper while being stronger than steel. Quantum dots, nanocrystals of semiconductors, manipulate light so precisely they're revolutionizing medical imaging and display tech. Even data storage has gone atomic. IBM demonstrated storing a bit of information on just 12 iron atoms, a staggering leap from the billions needed in traditional hard drives. This atomic precision extends beyond electronics. Catalytic converters transform car exhaust into harmless gases using platinum and palladium atoms as molecular matchmakers. Solar panels trap photons with silicon atoms tuned to specific energy levels. MRI machines rely on the quantum spin of hydrogen atoms in your body to create detailed internal maps. Each innovation reveals the same truth. The gap between raw elements and advanced technology isn't about finding new atoms, it's about learning to choreograph their interactions with ever greater finesse. Perhaps most remarkably, we're now entering the age of atomic fabrication. Scanning tunneling microscopes can nudge individual atoms into place, building structures atom by atom. Scientists have created designer molecules with custom properties, like artificial hemoglobin that binds oxygen more efficiently than the real thing. The emerging field of atomtronics aims to replace electrons with ultra-cold atoms in quantum circuits, potentially unlocking computers millions of times faster than today's. This isn't just progress, it's a fundamental shift in our relationship with matter. For billions of years, atoms assembled themselves through natural processes. Now, for the first time in cosmic history, they're being arranged intentionally by intelligent life. The microchip in your pocket represents a more intricate atomic arrangement than any meteorite or mountain. That's the paradox of technology. The more advanced it becomes, the more it returns us to the profound simplicity of atoms, the universal building blocks that, when understood deeply enough, can build anything we dare to imagine. Here's the cosmic twist: everything we've explored about atoms, from stardust to smartphones, accounts for less than 5% of the universe's total content. The rest, a cosmic ghost story, dark matter, an invisible substance that doesn't emit, absorb, or reflect light, outweighs atomic matter 5 to 1. It doesn't bond like carbon, conduct like copper, or glow like neon. In fact, it barely interacts with normal matter at all, except through gravity's silent tug. Picture a crowded room where you're the only person who can't see or touch anyone else, but you feel their weight pressing against you. That's how galaxies experience dark matter. The evidence for this elusive substance is etched into the cosmos itself. Stars orbit their galaxies too fast for visible matter alone to hold them in place, like a merry-go-round spinning so wildly its riders should fly off, yet something unseen keeps them anchored. Galaxy clusters bend light around them with gravitational force far beyond what their visible mass could produce, as if space itself is lined with hidden lead weights. Even the universe's large-scale structure, those vast filaments of galaxies stretching across billions of light years, couldn't have formed without dark matter's gravitational scaffolding. Atoms alone are too flimsy to build such cosmic architecture. What makes dark matter so baffling isn't just its invisibility, it's how fundamentally different it must be from atomic matter. Protons, neutrons, and electrons seem to play no part in its composition. Theories suggest it might consist of weakly interacting massive particles, actions, or even primordial black holes forged in the Big Bang's first second. Some experiments hunt for dark matter particles in abandoned gold mines, where ultra-sensitive detectors wait for the once-in-a-lifetime ping of a collision. Others scan the skies for anomalies in gamma rays or distortions in the cosmic microwave background, the afterglow of creation itself. Yet the most mind-bending possibility isn't just that dark matter exists, it's that our universe might host entire dark planets, dark stars, even dark life forms built from this shadow material. If dark matter interacts with itself through undiscovered forces, could it form complex structures without us ever noticing? Imagine a dark galaxy overlapping our Milky Way, its phantom stars neither burning nor fading, invisible neighbors passing through your body right now as effortlessly as wind through a screen door. This isn't science fiction, it's the cutting edge of physics. The Large Hadron Collider smashes particles at near light speed, hoping to create dark matter in miniature. Telescopes like the Vera Rubin Observatory map the cosmos in unprecedented detail, tracing dark matter's fingerprints in bent starlight. Every null result, every dead end, tightens the constraints on what dark matter can't be, inching us closer to understanding what it is. Atoms taught us that reality is built on hidden layers, first molecules, then subatomic particles, now this vast unseen ocean holding galaxies together. Dark matter humbles us, a reminder that for all our mastery over atoms, most of the universe remains a riddle wrapped in gravitational clues, and perhaps that's the most thrilling part. The cosmos still has secrets to spill, waiting for the right experiment, the right mind, the right moment to reveal what else or who else might be out there in the dark. Deep inside every star, a relentless atomic firestorm rages, one so powerful it can shine for billions of years. This isn't ordinary burning like wood in a fireplace. It's the alchemy of fusion, where hydrogen atoms crash together under such immense pressure and heat that they merge into helium, releasing staggering amounts of energy in the process. A single gram of hydrogen converted this way unleashes as much energy as burning 20,000 tons of coal. That's the cosmic efficiency of atomic power, and it's happening right now in our Sun, where 600 million tons of hydrogen fuse every second to bathe our solar system in warmth and light. What's astonishing is how simple the ingredients are. Stars start with the most basic atom, hydrogen, just one proton and one electron, and through nothing but gravity and time, they transform it into the stuff of planets and life. The core of a star becomes a factory where atoms are both the workers and the product, endlessly colliding and combining. When two hydrogen nuclei fuse, they don't just make helium, they release a tiny packet of pure energy in the form of light. Multiply that by the trillions upon trillions of reactions happening every moment inside a star, and you've got enough power to light up a galaxy. Here on Earth, we've learned to harness these atomic forces on a smaller scale. Nuclear reactors don't fuse atoms like stars do. They split them apart in a process called fission. When a uranium atom's nucleus is struck by a neutron, it becomes unstable and breaks into smaller fragments, releasing energy and more neutrons that trigger a chain reaction. A single uranium fuel pellet, no bigger than a pencil eraser, contains as much energy as a ton of coal. That energy heats water into steam, spins turbines, and powers cities without belching carbon into the atmosphere. It's star power in a concrete silo, proof that atoms are the ultimate batteries. But fusion remains the holy grail of energy science. For decades, researchers have tried to recreate the sun's conditions in machines like tokamaks, using magnetic fields to contain plasma hotter than the sun's core. The challenge is monumental, containing star-like temperatures without any material vessel melting, but the payoff would revolutionize civilization. Fusion promises clean, nearly limitless energy, with seawater as fuel and helium as the only byproduct. Recent breakthroughs like net energy gain experiments at facilities like the National Ignition Facility hint that this atomic dream might one day become reality. Even our everyday energy traces back to atomic interactions. The gasoline in your car, it's releasing energy stored in carbon-hydrogen bonds formed by ancient sunlight. The wind turning turbines, it's driven by temperature differences caused by, you guessed it, solar fusion. And those solar panels on rooftops, they're catching photons spat out by hydrogen-helium collisions 93 million miles away. Every watt of usable energy, from campfires to nuclear plants, is just atoms rearranging themselves to release stored power. This atomic energy dance extends far beyond Earth. When massive stars exhaust their fuel, they don't fade quietly, they explode as supernova, briefly outshining entire galaxies. In those final moments, they forge elements heavier than iron, from the gold in wedding rings to the iodine in your thyroid. Even the slow decay of radioactive atoms like uranium heats Earth's core, keeping continents drifting and volcanoes churning. Atoms aren't just passive building blocks, they're engines driving change across cosmic and human timescales. The next time you feel sunlight on your skin or switch on a light, remember, you're tapping into a cosmic inheritance written in atomic fire. Whether it's the gentle warmth of a summer day or the controlled fury of a reactor core, energy is atoms telling their story, one collision, one transformation at a time. And somewhere out there, new stars are igniting, continuing the cycle that began nearly 14 billion years ago, proving that the universe runs on an atomic heartbeat we've only begun to understand. The periodic table isn't finished, it's a living document, growing as scientists push atoms into uncharted territory. In laboratories around the world, researchers slam lighter elements together at nearly light speed, forging synthetic atoms that don't exist in nature. These super-heavy elements, like organesson with its 118 protons, survive for mere milliseconds before crumbling apart, yet their existence stretches our understanding of atomic stability. Imagine an architect designing a skyscraper so tall it collapses under its own weight. That's the delicate balance physicists navigate when creating elements beyond uranium. Each new addition to the table tests the limits of nuclear glue, hinting at an island of stability where even heavier atoms might persist long enough to reveal new chemical behaviors we can't yet predict. Quantum computing takes atomic manipulation to another level entirely. Instead of relying on silicon chips, these machines harness the bizarre behavior of atoms themselves, electrons spinning in two directions at once, particles entangled across distances. A single quantum bit or qubit can be an atom held in an electromagnetic trap or a superconducting loop mimicking atomic properties. Where classical computers plod through calculations one at a time, qubits explore countless possibilities simultaneously. It's like having a library where every book opens to all its pages at once, allowing answers to emerge from the quantum noise. Companies and governments are racing to scale these systems, knowing that a mature quantum computer could crack encryption, simulate complex molecules for drug discovery, or optimize global logistics in ways that would take conventional supercomputers millennia. Then there's antimatter, the ultimate atomic mirror. For every particle, nature created an opposite, positrons instead of electrons, antiprotons swapping negative for positive charge. When matter and antimatter meet, they annihilate in a flash of pure energy, making it the most potent fuel imaginable. Scientists at CERN produce antihydrogen atoms, painstakingly trapping them in magnetic bottles to study why the universe favors matter over its shadowy twin. 1 gram of antimatter contains the energy of 20 kilotons of TNT, enough to power a city for days, but producing even a billionth of a gram requires monumental effort. Yet this research isn't just about energy, it's probing cosmic origins. The Big Bang should have created equal amounts of matter and antimatter, leaving nothing but light. That we exist at all means some atomic asymmetry, some slight preference written into the laws of physics, tip the scales in matter's favor. Atomic precision is reaching staggering new heights. Microscopes now image individual atoms with such clarity that scientists can identify defects in materials, just one atom-wide flaws that might revolutionize electronics or battery tech. In medicine, proton therapy targets tumors with sub-millimeter accuracy, using hydrogen nuclei to destroy cancer cells while sparing healthy tissue. Even agriculture benefits, with nanoparticle fertilizers delivering nutrients directly to plant roots atom by atom, reducing waste and environmental harm. Perhaps most mind-bending is the prospect of designer atoms. Imagine tailoring elements with custom properties, superconductors that work at room temperature, materials that self-heal like skin, or catalysts that turn sunlight into liquid fuel with near-perfect efficiency. We're entering an era where understanding atomic behavior isn't enough. We're learning to rewrite the rules, from twisted graphene sheets exhibiting unheard-of conductivity to time crystals that oscillate without energy input. The frontier of atomic science isn't just about discovery, it's about reinvention. All this hints at a future where made of atoms might not mean what it does today. Quantum dots could assemble into programmable matter, shifting shape at will. Synthetic biology might redesign cellular machinery at the atomic scale to create new life forms. And someday, harnessing antimatter or zero-point energy could unlock propulsion systems capable of interstellar travel. The atoms that began in stars are now tools in human hands, and we're just beginning to learn what they can really do. Atoms have always been more than just scientific curiosities. They're mirrors reflecting our deepest hopes, fears, and creative impulses. Take the iconic imagery of atomic models, those elegant orbs and orbits that first appeared in textbooks and quickly leapt into galleries. Artist Julian Voss-Andri sculpts human figures from stainless steel quantum diagrams, turning atomic bonds into hauntingly beautiful silhouettes. His work captures the eerie truth that we're all walking constellations of particles, temporary arrangements of ancient stardust. Even the simplest atomic symbol, like the universal warning sign for radiation, has become cultural shorthand, evoking everything from Cold War anxiety to comic book superpowers. Literature and film have long wrestled with atomic duality, their power to both create and destroy. Godzilla, born from nuclear testing's aftermath, stomped through cinema as a walking metaphor for atomic dread. Meanwhile, Marvel's Ant-Man shrinks between atoms using fictional PIM particles, while the Hulk's origin story hinges on gamma radiation's transformative fury. These stories reveal our fascination with matter's hidden potential, imagining worlds where atomic mastery grants godlike abilities or unimaginable catastrophe. Philosophy orbits atoms just as tightly. Ancient Greek thinkers like Democritus dreamed them up millennia before microscopes could prove their existence, arguing reality was just atoms and the void. Today, quantum physics sparks modern Zen koans. If observing an atom changes its behavior, does consciousness shape reality? Artists like James Turrell play with this idea, using light installations that make viewers question whether they're seeing particles or waves, solidity or illusion. His work turns museum-goers into active participants in quantum uncertainty, blurring the line between observer and observed. Music pulses with atomic rhythms too. From Kraftwerk's Radioactivity to Muse's Supermassive Black Hole, artists weave atomic themes into lyrics and beats. Björk's album Biophilia literally vibrates with scientific inspiration, using app interactive songs to explore viral structures and cosmic cycles. Even children's toys like the once popular atomic purple Game Boy Color tapped into the sleek, futuristic allure of atomic aesthetics, transparent plastic mimicking the sea through excitement of peering into matter's building blocks. The atomic age reshaped design as thoroughly as it did physics. Mid-century, atom-punk architecture featured geodesic domes and molecular chandeliers, while Eames chairs borrowed their organic curves from electron probability clouds. Today, nano-artists like Luke Jerram craft glass sculptures of viruses millions of times their actual size, making the invisible tactile. His COVID-19 model, delicate as a Christmas ornament, reminds viewers that pandemics, like everything, begin at the atomic scale. Perhaps atoms resonate most deeply in how they've rewritten humanity's origin story. Knowing we're recycled starstuff transforms mythology into something grander than any ancient pantheon. Indigenous cosmologies like the Aboriginal concept of songlines or the Hindu notion of prana now find unexpected parallels in quantum physics. Modern poets like Alice Oswald write atomic elegies, describing a river's water molecules as a crowd of survivors clinging together. Even tattoo parlors see requests for Bower models and DNA helixes, permanent skin-deep reminders that we're never truly alone. We carry the universe's history in every cell. This cultural atomic fever isn't nostalgia, it's active reinvention. TikTok creators simulate quark interactions with dance trends, while bioartists like Joe Davis encode poetry into bacterial DNA. The Large Hadron Collider inspires fashion collections featuring collider ring dresses and particle collision prints. Everywhere, atoms remind us that science and art aren't opposites, they're twin lenses focusing on the same breathtaking truth. Whether through a painter's brush, a poet's stanza, or a physicist's equation, we're all trying to comprehend the same tiny marvels that build black holes, blue whales, and the device you're holding right now. Your body is a living, breathing testament to atomic recycling on a cosmic scale. Every second, you inhale oxygen atoms that once filled the lungs of dinosaurs, drink water molecules that flowed through ancient rivers, and consume carbon atoms that were once part of towering prehistoric ferns. The 7 octillion atoms currently assembling themselves into your cells aren't permanent residents, they're nomadic particles on loan from the universe, staying just long enough to power a thought, a heartbeat, or a blink before moving on to their next destination. Consider the oxygen entering your bloodstream right now. Some of those atoms might have been forged in a supernova explosion 5 billion years ago, drifted through interstellar clouds, then became part of Earth's early atmosphere. Others could have cycled through countless organisms before reaching you. Perhaps they once sustained a woolly mammoth's muscles or fueled the growth of a medieval oak tree. This constant exchange isn't poetic metaphor, it's measurable science. Isotope tracers reveal that 98% of your atoms are replaced annually, meaning the physical you from a year ago has literally dissipated into the environment, replaced by atoms from your meals, your showers, even the air you've breathed. The elements inside you tell a periodic table epic. The iron in your blood shares chemical fingerprints with meteorites that bombarded young Earth. The calcium strengthening your bones was likely deposited on ocean floors before tectonic shifts lifted it into mountains that eroded into soil. Even the zinc enabling your sense of taste might have been smelted in the furnace of a dying star 20 times more massive than our Sun. These atoms carry no memory of their origins, yet their very presence in your body connects you to events older than the solar system itself. Here's what's truly humbling. Your body contains more hydrogen atoms than there are stars in the observable universe. Those lightweight relics from the Big Bang form the water that comprises 60% of your weight, making you a walking reservoir of primordial matter. The carbon in your DNA, by contrast, is relatively new stellar alchemy, no older than 7 billion years, and the trace elements like copper and selenium. They're cosmic spices, rare ingredients sprinkled into your biological recipe by supernova and asteroid deliveries. This atomic turnover isn't just a curiosity, it's the reason life can adapt and persist. When cells divide, they don't reuse the same atoms like a car's engine recycling gasoline. They recruit fresh atoms to build new structures. This molecular refurbishment lets your body repair wounds, fight infections, and even rewire your brain when you learn. At this very moment, atomic construction crews are dismantling and rebuilding proteins in your muscles, neurotransmitters in your synapses, and pigments in your eyes, all without you ever noticing the renovation. The implications stretch beyond biology. Forensic scientists can trace your movements by analyzing isotopic signatures in your hair, which records the water you've consumed like atomic breadcrumbs. Archaeologists decipher ancient diets by measuring carbon isotopes in millennia-old bones. Even your breath contains clues. The carbon dioxide you exhale carries a distinct atomic fingerprint from the food that fueled its creation. You're not just made of atoms, you're a constantly updating atomic archive, writing your story one element at a time. Perhaps most astonishing is how this atomic flux creates continuity despite constant change. Like a river that remains the same while its water molecules ceaselessly flow, your identity persists even as your atomic constituents come and go. The atoms in your childhood body have long since scattered to winds and waterways, yet the pattern they once formed, your memories, your quirks, your laughter, somehow endures. This paradox is the magic trick at life's core, temporary assemblies of eternal particles creating something greater than their parts. So when you feel the weight of a long day or the thrill of a new idea, remember, you're not just reacting to the world around you. You're a symphony of stardust playing itself into existence moment by moment, a temporary constellation of atoms that will one day disperse to become mountain ranges, ocean currents, and perhaps even the shimmer in some future creature's eyes. The universe built you from its spare parts, and to the universe those parts will return, not as an ending, but as the next verse in an atomic song that began before time itself. Atoms may be the universe's ultimate building blocks, but they're not the whole story. For all their versatility crafting stars, planets, and even consciousness, they hit a wall when faced with some of existence's deepest puzzles. Take dark energy, the mysterious force accelerating the expansion of the cosmos. Atoms can't account for it. This invisible pressure makes up 68% of the universe's energy budget, yet it doesn't interact with light or matter in any way we've detected. It's as if the cosmos is being pushed apart by an unseen hand, and atoms, for all their complexity, are just passengers on this runaway ride. Black holes expose another atomic blind spot. At their cores lie singularities, points where gravity crushes matter into infinite density, tearing apart the very fabric of space and time. Here, the rules governing atoms break down completely. Protons, neutrons, and electrons cease to exist as recognizable entities. Even quantum physics stumbles in the face of such extremes. The equations that describe atoms so elegantly elsewhere simply scribble out into infinity, leaving us with a cosmic shrug. These gravitational monsters don't just bend the rules, they erase them, proving that atoms are local players in a much stranger game. Even within their own domain, atoms have boundaries. They can't explain why the universe favors matter over antimatter, a tiny imbalance that allowed anything to exist at all. They don't account for the eerie phenomenon of quantum entanglement, where particles influence each other instantly across vast distances, defying classical notions of cause and effect. And they're powerless to describe what happened in the first moments after the Big Bang, when temperatures were so extreme that atoms couldn't yet form. These gaps aren't failures, they're invitations. Every unanswered question about dark energy, singularities, or quantum weirdness hints at layers of reality beyond atomic structure. Perhaps strings vibrating in hidden dimensions, as string theory suggests, or parallel universes with entirely different physical laws. The fact that atoms can't explain everything doesn't diminish their brilliance. It underscores how much grandeur remains to be discovered. After all, the history of science is a story of peeling back layers, first discovering atoms, then subatomic particles, and now probing the weirder frontiers where even particles blur into waves of probability. So while atoms build the world we see and touch, they're also signposts pointing toward the profound unknown. They remind us that reality is richer and more mysterious than any single theory can capture, a tapestry still being woven with threads we've only begun to unravel. Atoms get all the glory when we talk about the building blocks of matter, but let's peel back the curtain. Inside every atom, there's a chaotic yet precise dance of even tinier particles, quarks whirling inside protons and neutrons, electrons buzzing in probability clouds. So why don't we say everything is made of quarks or electrons instead? It's not just about size, it's about stability and identity. Quarks, for instance, are never found alone in nature. They are forever bound together by the strong nuclear force, like cosmic Velcro, forming protons and neutrons that then assemble into atomic nuclei. Electrons, while more independent, don't carry the full recipe of an element on their own. An atom, though, it's the smallest package that still says, "I'm gold" or "I'm oxygen" with unwavering certainty. Think of it like baking. Flour, eggs, and sugar are the fundamental ingredients, but you wouldn't call a cake flour or a cookie sugar. Those raw materials lose their individual identities when they combine into something new. Similarly, quarks lose their solo relevance once they team up inside protons. It's the arrangement of those particles, the specific number of protons in a nucleus, that defines an element's personality. A single proton is just hydrogen. Add 6 more, and suddenly it's nitrogen. Atoms are nature's way of organizing chaos into recognizable, functional matter. Here's where things get even more interesting. Subatomic particles are like frenetic backstage crew, essential but invisible to the audience. They don't dictate how matter behaves in everyday life. Atoms do. When you touch a table, it's the electromagnetic force between atoms that makes it feel solid, not the quarks inside them. When you breathe, it's oxygen atoms bonding with hemoglobin, not lone electrons doing the heavy lifting. Atoms are the smallest units that reliably participate in chemical reactions, hold shapes, and carry properties we can observe without particle accelerators. That's not to say subatomic particles aren't important. They're the reason atoms exist at all. The strong force binding quarks is 100 times more powerful than electromagnetism, which is why atomic nuclei stay intact despite the repulsion between positively charged protons. But that same force has a vanishingly short range, like a superhero who can only save the day within arm's reach. Once you zoom out to atomic scales, electromagnetism takes over, governing how atoms interact, bond, and build the world we see. This division of labor explains why chemistry and particle physics feel like separate worlds. Chemistry is the science of atoms and their alliances. Particle physics digs into the subatomic frenzy beneath. Both are valid, just focusing on different levels of reality. It's like studying a city. You could analyze individual bricks' quarks, but you'd miss the architecture of buildings' atoms. Or you could admire the skyline molecules without worrying about what each brick is made of. Atoms strike the perfect balance, complex enough to create diversity, simple enough to follow predictable rules. So while quarks and electrons are the universe's raw materials, atoms are its lingua franca. The common tongue matter speaks when it wants to build planets, proteins, or people. They're nature's sweet spot between simplicity and complexity, the smallest units that still make sense to us in a tangible, touchable way. And that's why, even in a world teeming with smaller particles, atoms remain the stars of the show. Long before microscopes or particle accelerators, a Greek thinker named Democritus stared at a seashell crumbling in his hand and imagined the unseeable. If he kept breaking that shell into smaller and smaller pieces, he reasoned, there must be a point where it couldn't be divided further, an uncuttable unit he called atomos. This wasn't just proto-science, it was a revolutionary leap of logic, suggesting reality had building blocks too small for the eye. What's remarkable isn't that he got the details wrong. His atoms hooked together like tiny burrs, a far cry from quantum clouds, but that he grasped the essential truth: complexity arises from simplicity. 24 centuries later, atoms still straddle the line between science and philosophy. They force us to confront uncomfortable questions like whether the solid table you're resting your hands on is truly solid at all. At the subatomic level, it's a buzzing void where particles flicker in and out of existence. So why does it feel so unyielding? The answer lies in the electromagnetic fields generated by those very atoms, repelling your hand's atoms with invisible force. What we perceive as touch isn't contact but resistance, a cosmic game of keep-away played by particles that never truly meet. This illusion of solidity makes you wonder, is reality just a series of carefully orchestrated misunderstandings? Modern physics compounds the mystery. Quantum mechanics reveals that atoms don't behave like miniature billiard balls, but as probability waves, ghostly tendencies rather than definite things. An electron doesn't orbit a nucleus the way planets circle the sun. It occupies a smear of possible locations until observation snaps it into place. This isn't just academic nitpicking, it undermines our instinctive sense of how objects should work. If the foundation of matter is fundamentally fuzzy, what does that say about the reliability of the world we experience? Artists like Salvador Dali intuited this decades before quantum theory, painting melting clocks and floating rocks that captured matter's unsettling mutability. Perhaps the most humbling realization is that atoms might not be the final layer. String theory suggests they're composed of vibrating filaments of energy, tiny loops dancing in 11 dimensions. Other models propose that spacetime itself is pixelated, with atoms emerging from a deeper code like images on a screen. Even dark matter hints that atoms are just the visible tip of a cosmic iceberg, overshadowed by 5 times more unseen substance. Democritus would likely cheer these developments. His genius wasn't in nailing the specifics, but in recognizing that reality rewards those who question surfaces. This atomic uncertainty mirrors human experience. We build identities from shifting memories, societies from fragile agreements, all temporary arrangements of deeper, stranger truths. Just as atoms assemble into momentary forms, a raindrop, a fingerprint, a supernova, we too are patterns in the cosmic flux. The ancient Greeks sought atoms to explain permanence amid change, but today they remind us that impermanence is the only constant. Every breath you take disperses atoms you'll never reclaim, while gathering new ones destined to become part of someone or something else. In that endless exchange, perhaps, lies the real philosophy of atoms, not just how matter works, but what it means to be a fleeting configuration in an infinite rearrangement. Atoms may seem indestructible in our everyday world, but throw them into the heart of a neutron star, and they undergo a metamorphosis so radical it rewrites the rules of matter itself. Picture this: a teaspoon of neutron star material would weigh about 6 billion tons on Earth, the same as Mount Everest squeezed into a sugar cube. Under that unimaginable pressure, atoms don't just get squished, they surrender completely. Electrons are slammed into protons, merging to form neutrons, while the empty space that normally defines an atom collapses into an ultra-dense neutron soup. What was once a structured system of nuclei and orbits becomes a single, seething mass of nuclear particles, packed so tightly they behave more like a superfluid than solid matter. Even here, though, atoms leave their fingerprints. The neutron stars crushing gravity and magnetic fields are direct relics of the atomic forces that once were. Black holes take atomic annihilation even further, cross the event horizon, and atoms don't just compress, they're unraveled into their fundamental components. The gravitational tides near a black hole singularity are so intense they stretch atoms into spaghetti-like strands in a process called spaghettification. Protons, neutrons, and electrons are torn apart, then further dissected into quarks and gluons. Eventually, even those particles may lose their identity, merging into a singularity where the very concepts of particle or atom cease to have meaning. It's the ultimate cosmic shredder, reducing matter to its most abstract form. Yet paradoxically, black holes also create environments where atoms are reborn. In the swirling accretion disks of supermassive black holes, temperatures reach trillions of degrees, forging heavy elements like gold and platinum in violent collisions, proof that even in destruction, atoms find ways to reassert their role as universe builders. These extremes reveal a startling truth: atoms are both fragile and unyielding. In the vacuum of space, a lone hydrogen atom can drift undisturbed for billions of years. But place it in the core of a collapsing star, and it becomes part of a transformational alchemy. The same atomic bonds that snap easily under human-scale forces become nearly unbreakable in the heart of a white dwarf, where electron degeneracy pressure defies gravity's crush. It's as if atoms have multiple personalities, docile builders in one environment, indomitable survivors in another. Even in the most hostile corners of the cosmos, they adapt. The carbon in your DNA, the iron in your blood, these elements were forged in environments that should have annihilated them, yet here they are, woven into the fabric of life. What's most humbling is how these atomic extremes connect to us. The gold in a wedding ring likely formed when two neutron stars collided, sending ripples of heavy elements across the galaxy. The uranium powering nuclear reactors spent its infancy in the aftermath of supernova. Atoms teach us that the universe's most violent events aren't just destructive, they're creative acts scattering the ingredients for planets and life across the cosmos. So while a neutron star or black hole might seem like the end of an atom story, it's really just a chapter in a much grander saga. One where destruction and creation are two sides of the same cosmic coin. Atoms hold time in their nuclei like tiny hourglasses, some counting seconds, others ticking through billions of years. Consider the hydrogen in your body's water molecules. Those atoms have likely existed unchanged since the universe's first 3 minutes, silent witnesses to the birth of galaxies. Carbon atoms in your DNA might be mere billions of years younger, forged in stars that died before Earth formed. On cosmic scales, atoms are nearly immortal, endlessly recycled through supernova, solar winds, and the slow grind of tectonic plates. Yet this permanence is an illusion when you peer into the atomic core. Radioactive elements like uranium-238 measure time in a different language, one where stability is fleeting and decay is inevitable. Take a uranium atom buried deep in Earth's crust. Its nucleus, packed with 92 protons and 146 neutrons, is a monument to precarious balance. Quantum mechanics dictates that even such a massive nucleus isn't immune to change. Every so often, precisely every 4.5 billion years on average, half of any uranium sample will spontaneously transform. A neutron splits into a proton and electron, turning uranium into thorium while releasing energy. This isn't destruction, it's metamorphosis. The same thorium might later become radium, then radon, marching down the decay chain until settling as lead. That lead, now stable, could lie dormant for eternity or get swept up into a future supernova, where extreme conditions might reforge it into something new. This decay isn't random chaos. It follows exponential predictability so reliable we use it as a clock. Geologists date Earth's oldest rocks by measuring uranium to lead ratios, just as archaeologists use carbon-14 steady decay to pinpoint ancient fires or bones. The carbon-14 in your body, absorbed from food and air, is disappearing at a rate of about 1% every 80 years. Yet this fleeting isotope connects you directly to cosmic processes. It's created when cosmic rays strike nitrogen atoms in the upper atmosphere, a reminder that even our atomic clocks are wound by starlight. The contrast between stable and radioactive atoms reveals a deeper truth about the universe's architecture. Iron-56 sits at the peak of nuclear stability. Its nucleus is so tightly bound that splitting or fusing it consumes energy rather than releasing it. That's why stars accumulate iron in their cores like ash in a furnace, and why supernovae are needed to forge anything heavier. Elements like gold or platinum exist because dying stars provided the unimaginable energies required to push nuclei beyond iron's comfort zone. These rarer atoms are essentially cosmic overachievers, clinging to existence despite their innate instability. Even ostensibly stable atoms aren't truly permanent. Protons, the bedrock of atomic identity, may eventually decay, though if they do, it would take longer than the current age of the universe to notice. Some grand unified theories predict protons will disintegrate after 10 to the power of 34 years, leaving behind only leptons and photons. In that distant era, even iron atoms would evaporate like morning dew, marking the end of atomic matter as we know it. Yet against this staggering timeline, human history is less than a blink, a fleeting moment where atoms briefly assembled into beings capable of pondering their own impermanence. What's beautiful is how atoms turn decay into creation, the heat that keeps Earth's core molten, mostly from uranium and thorium atoms breaking down. The neon glow of auroras, solar particles exciting oxygen and nitrogen atoms in our atmosphere. Every banana emits radiation from its potassium-40 content about 15 decays per second, a harmless reminder that atoms are never truly still. Even our sun owes its shine to a kind of decay. Hydrogen nuclei fusing into helium is fundamentally about protons transforming into neutrons, shedding energy as they go. So when we say atoms are eternal, we're really talking about resilience through transformation. They teach us that change isn't the opposite of existence, it's the mechanism. Whether surviving unaltered for billions of years or actively unraveling in measurable time, atoms embody the universe's grand improvisation, endlessly rearranging itself, using the same notes to compose new songs. The uranium in your granite countertop, the carbon in your morning coffee, the argon in the air you breathe, they're all verses in an atomic epic where time isn't a destroyer but an alchemist. Scientists are now playing cosmic architect, constructing synthetic atoms in laboratories that bend the rules of nature itself. These aren't just imitations of natural atoms, they're entirely new configurations, engineered with precision to exhibit properties you'd never find in the wild. Picture a quantum dot, a nanocrystal so small it confines electrons in ways that mimic atomic behavior, but with a twist. Adjust its size by a few nanometers, and you can fine-tune the color of light it emits like a microscopic mood ring. These artificial atoms are proving that the periodic table isn't the final word on matter, it's just the opening chapter. What makes these lab-grown atoms revolutionary isn't just their novelty, it's their customizability. Traditional atoms come with fixed properties dictated by their proton count, but synthetic versions let researchers dial in specific quantum behaviors on demand. Take superconducting circuits, where microwave photons trapped in tiny loops act like artificial atoms with energy levels that can be precisely manipulated. Unlike their natural counterparts, these designer atoms can be coaxed into quantum superpositions existing in multiple states simultaneously for far longer than naturally possible, a feature that's turning them into the building blocks of quantum computers. Medicine is already reaping the benefits. Quantum dots injected into the bloodstream can tag cancer cells with fluorescent precision, lighting up tumors for surgeons with unprecedented clarity. Meanwhile, artificial atoms embedded in biosensors detect single molecules of viruses or pollutants, offering diagnostics so sensitive they border on clairvoyance. Even energy storage gets a boost. Synthetic atoms in next-gen solar cells absorb wavelengths of light that silicon can't touch, squeezing more electricity from every photon. The real magic happens when these synthetic atoms start communicating. In nature, atoms interact through rigid rules, covalent bonds here, ionic attractions there. But engineered atoms can be programmed with entirely new languages. Some communicate through entangled photons, linking across distances instantaneously. Others exchange information via phonons, vibrational waves, opening doors to heat-based computing. It's as if we've been given access to the universe's source code, allowing us to rewrite the scripts that govern how matter behaves. This isn't just about improving existing tech, it's about inventing categories that don't yet exist. Imagine materials that change their atomic structure on command, becoming conductors or insulators at will. Or quantum networks where information teleports between nodes encoded in synthetic atoms, making today's internet look like Morse code. The line between the natural and the artificial is blurring, revealing a future where atoms aren't just discovered. They're designed with purposes as specific as the microchips in your phone or the drugs in your pharmacy. Yet for all their potential, these lab-grown atoms carry a humbling reminder. Their very existence proves that nature's toolkit isn't the only way to assemble reality. The same quantum rules that shaped stars and planets can be harnessed to create structures no star ever dreamed of, not by breaking the laws of physics, but by exploring corners of them the universe hasn't yet bothered to visit. In that sense, every synthetic atom is both an invention and a discovery, a human-made creation that reveals just how much wonder still hides in the spaces between the known and the possible. Long before microscopes revealed their true nature, atoms danced through human imagination as fragments of the divine. The ancient Vedic texts of India spoke of Anu, uncuttable particles that formed the essence of all matter, while Buddhist philosophers described reality as a flickering stream of kalapas, momentary clusters of elemental energy. These weren't primitive guesses at scientific truth, but profound metaphors for existence itself, recognizing that beneath life's apparent solidity lay something more fundamental. The Greek philosopher Leucippus and his student Democritus took this further, envisioning atoms as eternal, indestructible seeds from which all variety sprang: hard atoms making earth, smooth ones creating water, and fiery ones forming the soul. Across the Pacific, the Aztecs told of Tezcatlipoca, the smoking mirror god who shaped the world from competing elemental forces. His rival Quetzalcoatl breathed life into human bones by sprinkling them with sacred ground maize, a poetic parallel to how carbon atoms build living tissue. In West Africa, the Yoruba creation story describes the supreme deity Olodumare scattering as divine energy like cosmic dust to form the universe, while Norse mythology imagined the primordial giant Ymir's body becoming the world itself, his flesh the soil, his bones the mountains, his blood the seas. These myths share an uncanny intuition. That complexity arises from simple, repeating units arranged in infinite combinations. The Chinese concept of Wu Xing, the 5 phases of wood, fire, earth, metal, and water might seem distant from atomic theory until you consider how these elements were believed to transform into one another through cycles of conquest and nurture. This mirrors how real atoms bond and break apart in chemical reactions, with oxygen conquering hydrogen to form water or carbon, nurturing long molecular chains. Alchemists in medieval Europe took this further, seeking not just to transmute lead into gold but to uncover the prima materia, the ultimate substance from which all diversity flowed. Their elaborate symbolism, full of serpents swallowing their tails and hermaphroditic beings, encoded a startling truth: matter's unity beneath its apparent divisions. Even Abrahamic traditions carried atomic echoes. Jewish mysticism's Sephirot depicted divine energy crystallizing into material forms, while some Islamic scholars, like the Brethren of Purity, described the world as nested layers of organization from particles to planets. Christianity's Eucharist, where bread and wine become sacred while retaining their appearance, hints at a universe where surface and substance can diverge, much like how atomic arrangements determine a material's properties regardless of its visible form. What's remarkable isn't how wrong these ancient models were, but how they grasped the essential poetry of atoms, their dual role as both physical stuff and metaphysical principle. When the Hindu Upanishads declare all this is Brahman, or the pre-Socratic Heraclitus observes that everything flows, they're articulating a truth modern physics confirms, that solidity is an illusion and change is the only constant. The Hopi people's belief that all matter contains Kachina, life force, mirrors quantum field theory's vision of particles as excited states of underlying energy. These myths endure because they satisfy a deep human need to find meaning in matter's building blocks. Science tells us iron atoms carry oxygen in our blood, but mythology reminds us that the same iron fell from supernova as the blood of gods. Carbon becomes not just a chemical element but the ink with which the universe writes its stories. In this light, the ancient vision of atoms as divine sparks wasn't primitive science. It was early recognition of their true wonder. After all, what else but something miraculous could take the form of stars, stones, and sentient beings all at once? The myths got the details wrong, but the grandeur right. Atoms really are the universe's way of knowing itself, one temporary arrangement at a time. Think about the last time you heard music, the deep thump of a bass line vibrating your chest or the crisp ring of a bell cutting through the air. That sound wasn't magic, it was atoms in motion. Every note, every whisper, every crash of thunder is just a chain reaction of atoms bumping into each other, passing energy along like a cosmic game of telephone. When a guitar string plucks, it jostles air molecules which collide with their neighbors in a wave that eventually reaches your eardrum. No atoms, no sound. The universe would be as silent as a vacuum because sound needs matter to dance through. This atomic relay race works differently depending on the medium. In air, sound moves like a slinky being stretched and compressed. Air molecules crowd together in some spots compressions and spread out in others rarefactions, creating pressure waves that travel at about 767 miles per hour. But dive underwater and sound suddenly moves 4 times faster because water molecules are packed tighter, passing vibrations more efficiently. Ever press your ear to a train track to hear an approaching locomotive before it's visible? That's sound exploiting the rigid atomic lattice of steel, where vibrations race ahead at over 3,000 miles per hour. Solids are nature's megaphones, their tightly bonded atoms transmitting energy with barely any loss. What's wild is how specific atomic arrangements create unique sounds. A diamond and a lump of graphite are both pure carbon, but their atomic structures couldn't be more different. Strike a diamond and its rigid tetrahedral lattice rings with a clear, glassy ping. Graphite, with its slippery layers of carbon sheets, just gives a dull thud. Even in metals, tiny atomic imperfections, missing atoms or foreign ones, can deaden vibrations, which is why pure copper bells sing clearer than cheap alloys. Piano makers have exploited this for centuries, selecting woods and metals not just for strength, but for how their atomic structures shape timbre and sustain. The absence of atoms reveals sound's limits. In deep space where atoms are scarce, explosions happen in eerie silence. Sci-fi movies get this wrong all the time. No air means no sound, no matter how epic the supernova. But spacecraft like NASA sonification projects translate electromagnetic vibrations from celestial objects into audible frequencies, letting us hear galaxies or nebulas through artificial means. It's a reminder that sound, as we know it, is an earthly phenomenon, a quirk of atomic interactions that might be utterly alien on planets with different atmospheres or none at all. Yet atoms don't just carry sound, they create it. When a violin bow drags across a string, it's not just moving air, it's exciting specific resonant frequencies in the wood's atomic structure, a phenomenon called eigenmodes. The same principle gives each person's voice its unique fingerprint. Your vocal cords vibrate air, but your throat, mouth, and nasal cavities, each with their own atomic makeup, filter and amplify certain frequencies. Even the pop of a champagne cork comes from trillions of CO2 molecules suddenly escaping their liquid atomic cage, creating a pressure wave we recognize as celebration. This atomic symphony extends beyond human perception. Bats navigate with ultrasonic clicks bouncing off moth wings, whose scales are tuned to scatter sound at specific frequencies, an evolutionary arms race played out in atomic vibrations. Earthquakes send infrasound rumbles through the planet's crust, frequencies too low for our ears but sensed by elephants and even some birds. And at the quantum scale, scientists now listen to the sound of individual atoms moving using atomic force microscopes, turning subatomic shifts into audible clicks and hums. So next time you clap your hands or hear rain on a roof, remember, you're not just hearing noise, you're witnessing atoms talk to each other, relaying messages across space and time. From the first cry of a newborn to the last note of a symphony, sound is atoms keeping rhythm with the universe, one vibration at a time. At the heart of every interplanetary mission ticks an atomic clock so precise it could run for millions of years without losing a second. These aren't your grandfather's pendulum clocks, they're devices that harness the unshakable rhythm of atoms themselves, typically cesium or rubidium, whose electrons flip between energy levels with metronomic regularity. When NASA Voyager probes crossed into interstellar space or when the Perseverance rover landed flawlessly on Mars, their navigation depended on these atomic timekeepers. Here's why space navigation boils down to timing signals exquisitely well. A spacecraft's radio signal, traveling at the speed of light, takes about 20 minutes to reach Earth from Mars. A timing error of just 1 microsecond translates to a navigation error of 300 meters enough to miss a landing zone entirely. Atomic clocks aboard spacecraft and on Earth synchronize these signals, letting engineers triangulate positions across millions of miles with the precision of a cosmic surveyor. But atoms don't just keep time for space travel, they might power it. Traditional chemical rockets, like those that launched Apollo missions, are fundamentally limited by the energy stored in molecular bonds. Nuclear propulsion, by contrast, taps into the far greater energy locked inside atomic nuclei. Imagine a spacecraft like NASA's planned Draco mission, where uranium atoms split in a reactor, heating hydrogen propellant to temperatures no chemical engine could withstand. This isn't science fiction, it's physics. Fission fragments from split uranium atoms carry millions of times more energy per particle than burning rocket fuel, potentially cutting travel time to Mars from months to weeks. And if we ever crack nuclear fusion, the same process that powers stars' interstellar travel inches closer to reality. The Breakthrough Starshot initiative even envisions using ground-based lasers to push light sails attached to gram-scale probes, accelerating them to a fifth of light speed using nothing but photons, the quantized energy packets of light itself. Beyond propulsion, atoms are the silent cartographers of the cosmos. Spectrometers aboard probes like ESA's Rosetta or NASA's Juno don't just photograph alien worlds, they dissect starlight and reflected sunlight to reveal the atomic makeup of comet tails or Jupiter's atmosphere. When the James Webb Space Telescope detects water vapor on distant exoplanets, it's spotting the specific infrared wavelengths absorbed by H2O molecules. Every element leaves a fingerprint in light, and by reading these spectral lines, we've discovered metal vapors in Mercury's exosphere, organic molecules in Saturn's moon Enceladus, and even sodium glowing in the tail of an interstellar visitor like Oumuamua. The future of space exploration might lie in harnessing atoms even more intimately. Ion thrusters, already used in missions like Dawn and Deep Space One, strip electrons from xenon atoms, then accelerate the resulting ions with electric fields to velocities 10 times higher than chemical rockets achieve. These engines sip fuel but thrust continuously for years, making them ideal for deep space missions. Meanwhile, theoretical antimatter drives still far beyond our reach would annihilate hydrogen atoms with their antimatter counterparts, converting 100% of their mass into energy via Einstein's E equals mc2. Just 10 grams of antimatter could propel a crewed ship to Mars in weeks, but producing and storing even a billionth of a gram remains a monumental challenge. Perhaps most poetically, atoms are the bridge between Earth and the stars, the gold shielding on spacecraft electronics, forged in neutron star collisions billions of years ago. The aluminum in hulls, once part of asteroids that avoided becoming planets. Even astronauts themselves are temporary assemblies of atoms that once cycled through supernova and comets before joining this unprecedented journey. Every space mission is, at its core, atoms from ancient cosmic events now venturing back into the void, carrying with them the curiosity of a species just beginning to understand its atomic ancestry. As we look toward lunar bases and Martian colonies, atoms will play even more surprising roles. 3D printers may sinter lunar regolith, dust rich in aluminum, silicon, and titanium, into habitats without hauling materials from Earth. Nuclear batteries powered by plutonium-238 steady decay will heat rovers on icy moons where sunlight is faint. And if we ever discover life beyond Earth, its atomic composition, whether silicon-based or swimming in ammonia, will rewrite our understanding of matter's possibilities. The universe built us from star stuff, and now we're using that same star stuff to explore it, a homecoming written in the language of atomic physics. Press your hand against a table. What you feel as unyielding solidity is one of nature's greatest magic tricks. At the atomic level, that table is less like a dense slab of wood and more like a swarm of hyperactive bees buzzing around an empty warehouse. If you could shrink down to the size of an atom, you'd find yourself in a dizzying void where the nucleus of each atom is a grain of sand suspended in a cathedral, with electrons zipping around it at nearly the speed of light. The distance between these particles is so vast that if the nucleus were the size of a basketball, the nearest electron would be orbiting over 6 miles away. This means the table and your hand are both over 99.9% empty space. So why does anything feel solid at all? The secret lies in the electromagnetic force, nature's ultimate illusionist. Every electron carries a negative charge, and since identical charges repel each other, the electrons in your hand's atoms refuse to get too close to the electrons in the table's atoms. It's like trying to push two powerful magnets together with the same poles facing. They resist with an invisible force field. What you perceive as the table's solidity is really just a relentless electromagnetic pushback, a cosmic standoff between charged particles that never actually touch. This revelation flips everyday intuition on its head. The floor holding you up, the phone in your palm, even the bones beneath your skin, none of them are truly solid in the way we imagine. Instead, they're intricate force fields, more akin to standing on a densely woven net than a concrete slab. Even steel, the epitome of industrial strength, derives its toughness not from being packed wall to wall with matter, but from the way its atoms share electrons in a flexible lattice, creating a collective resistance to deformation. The illusion becomes even stranger when you consider light. A pane of glass feels solid, yet photons slip through it effortlessly, because their energy doesn't interact with the electrons in the glass's atomic structure. Conversely, a concrete wall blocks light not because it's more solid, but because its atoms absorb and scatter photons. This selective interaction hints at a deeper truth. Solidity isn't an absolute property. it's a relationship between matter and the forces acting upon it. Quantum mechanics adds another layer of weirdness. At subatomic scales, particles don't behave like tiny billiard balls but as probability clouds. When two objects touch, their electron clouds overlap, creating a statistical chance of interaction rather than a definitive collision. In a sense, every physical contact is a ghostly handshake, mediated by probabilities and electromagnetic whispers. This atomic emptiness has cosmic implications. Neutron stars, the densest objects besides black holes, are what happens when gravity overpowers electromagnetic repulsion, crushing atoms until electrons and protons merge into neutrons. A sugar cube of neutron star material would weigh as much as Mount Everest, proving how much nothing normally fills the space inside matter. Yet here on Earth, that emptiness is precisely what allows chemistry and life to exist. If atoms were truly solid, they'd clump together like putty, unable to form the dynamic bonds that build DNA, water, or proteins. The next time you lean against a wall or grip a coffee mug, remember, you're not interacting with objects so much as orchestrating an intricate quantum ballet. What feels like firm reality is really a delicate equilibrium of forces, a dance of charged particles spinning in a void. The universe could have been packed shoulder to shoulder with matter, a claustrophobic plenum where nothing moved. Instead, it chose emptiness and energy, crafting the illusion of solidity from the interplay of invisible fields. In that choice lies the possibility of stars, planets, and beings complex enough to question the nature of the very ground beneath their feet. Picture a neon sign buzzing to life in a city alley. Its vibrant glow isn't just electricity, it's atoms putting on a light show. Inside that glass tube, neon atoms get jazzed up by electrical energy, their electrons leaping to higher orbits like climbers scaling rungs on a ladder. But these excited electrons are fidgety, they can't stay elevated for long. When they tumble back down, they release that extra energy as photons, specifically crimson light at a wavelength of 632 nanometers. This atomic acrobatics isn't unique to neon. Every element in the periodic table has its own signature moves, dictated by the precise energy gaps between its electron orbits. Sodium's downward electron hops emit the fiery yellow of street lamps, while coppers produce the eerie green-blue of fireworks. This dance between atoms and light isn't confined to human inventions, it's the universe's favorite art form. Auroras paint polar skies because solar wind particles slam into oxygen and nitrogen atoms high in Earth's atmosphere. Oxygen's electrons, when struck just right, relax by emitting emerald or ruby light depending on altitude, while nitrogen contributes purples and blues. Even the sun's golden hue comes from hydrogen atoms in its outer layers absorbing and re-emitting light in a process called scattering, filtering out blues and leaving warm tones. Stretch this phenomenon across galaxies, and you get cosmic rainbows. Nebulas like Orion glow pink thanks to hydrogen's electron transitions, while sulfur adds mustard yellows and oxygen chips in teal. What's mesmerizing is how this atomic light code lets us decode the cosmos. Telescopes don't just collect starlight, they dissect it into spectral barcodes. When astronomers spot dark lines in sunlight called Fraunhofer lines, they're seeing atoms in the sun's cooler outer layers gobbling up specific wavelengths. Each element absorbs light at fingerprints unique as a snowflake. Calcium snags violets, iron grabs dozens of colors, and helium, first discovered in the sun's spectrum before being found on Earth, claims a sunny yellow line at 587 nanometers. This is how we know stars are mostly hydrogen, how we've detected titanium oxide in exoplanet atmospheres, and how neon earned its name. It means new one, after its spectral lines revealed an unknown element. But atoms don't just absorb and emit light, they can twist it too. A prism splits white light because atoms in glass slow down photons differently depending on wavelength, bending violets more than reds. More bizarrely, some crystals exhibit fluorescence, where ultraviolet light excites atoms to emit visible glow. Think blacklight posters or scorpions shining eerie blue under UV. Even the blue of a morpho butterfly's wing isn't pigment but nanostructures tuned to interfere with light waves, proving nature mastered atomic optics long before we did. Yet the grandest light show might be inside you. The red of blood comes from iron in hemoglobin absorbing blue-green light, while melanin's broad absorption spectrum gives skin its tones. Your ability to see color at all relies on retinal molecules changing shape when struck by photons, a direct atomic interaction triggering electrical signals interpreted as scarlet sunsets or verdant forests. In this way, light and atoms conspire to paint not just the cosmos, but the very canvas of human perception. Atoms aren't just passive building blocks in your body, they're active healers, warriors, and spies in modern medicine. Take radiation therapy, where high-energy particles bombard cancerous tissue with atomic precision. These aren't random explosions, it's a calculated strike. X-rays or gamma rays knock electrons clean off atoms inside cancer cells, ionizing them and shredding their DNA like a molecular blender. The genius lies in selectivity. Cancer cells divide rapidly, making them more vulnerable to this atomic sabotage than healthy tissue. But here's the twist: newer techniques like proton therapy go even further. Instead of photons, they fire hydrogen nuclei stripped of their electrons. These charged protons dump most of their energy at a specific depth, like a depth charge for tumors, minimizing collateral damage to surrounding organs. It's atomic warfare at the cellular level, with precision that would make a sniper envious. Meanwhile, MRI machines turn atomic behavior into a diagnostic superpower. Your body's hydrogen atoms, especially those in water and fat, act like tiny compass needles spinning in the machine's monstrous magnetic field, thousands of times stronger than Earth's. When hit with radio waves, these hydrogen protons flip their spins like gymnasts, then relax back into alignment, emitting signals as they go. Sensors decode these atomic echoes into breathtakingly detailed images of your brain's folds or a beating heart's chambers. What's astonishing isn't just the resolution. It's that MRI detects differences in how atoms behave in healthy versus diseased tissue. Tumors, inflamed joints, or torn ligaments all subtly alter how hydrogen's protons dance, revealing problems long before symptoms arise. But atoms don't just fight disease, they track it. PET scans use radioactive isotopes like fluorine-18, which decays by emitting positrons. When these antimatter particles meet electrons in your body, they annihilate in a burst of gamma rays, pinpointing metabolic hotspots where cells greedily consume sugar. Cancer cells, with their frenzied growth, light up like Christmas trees on these scans. Even simpler isotopes play vital roles. Technetium-99m, a nuclear isomer, helps map blood flow through the heart, while iodine-131 hunts down overactive thyroid cells like a microscopic heat-seeking missile. The frontier of atomic medicine is now crossing into the quantum realm. Nanoparticles laced with rare earth atoms can be guided to tumors, then heated with infrared light to cook cancer from within. Quantum dots, artificial atoms engineered to glow when struck by light, tag individual cancer cells during surgery, helping surgeons remove every last trace. And researchers are even exploiting atomic vibrations. Raman spectroscopy detects the unique fingerprint of molecules by how their atoms scatter laser light, potentially diagnosing infections from a single drop of blood. Yet for all this high-tech wizardry, the most profound atomic medicine might be the oldest. Lithium, the third lightest element, stabilizes mood disorders by mechanisms we're still unraveling, possibly by altering how sodium and potassium atoms shuttle across brain cell membranes. Iron atoms in hemoglobin have carried oxygen for 500 million years, while zinc's electrons catalyze over 300 enzymes keeping you alive daily. From the calcium strengthening your bones to the potassium fueling your nerves, you're literally a walking periodic table of atomic remedies. What's humbling is how these medical miracles hinge on cosmic accidents. The iodine in your thyroid likely formed in a dying star's last gasp. The uranium that powers some cancer treatments is ancient stardust, decaying on a timetable set at the dawn of the solar system. Even the hydrogen imaged in MRIs is primordial, unchanged since the Big Bang. Atoms remind us that healing isn't just biology, it's physics, chemistry, and astronomy converging in every hospital room. The same particles that once burned inside stars now mend broken bones, illuminate injuries, and hunt disease, proving that the universe packed its building blocks with unexpected purpose. Every time you stream a movie or video call a friend, you're riding waves of light meticulously guided by the atomic structure of silicon, the unsung hero of the Internet's backbone. Fiber optic cables, those hair-thin strands of glass, work because silicon dioxide atoms arrange themselves into a crystal lattice so orderly it can steer photons like a subway track for light. The core of these cables is doped with germanium or fluorine atoms, subtly altering how light refracts to keep signals from leaking out. It's a feat of atomic precision. Photons encoded with data zigzag through the glass, bouncing off the walls at shallow angles, their path dictated by the precise spacing between silicon and oxygen atoms. A single cable thinner than a drinking straw can carry thousands of simultaneous conversations, all because atoms were coaxed into the perfect alignment to corral light. But silicon isn't the only atomic workhorse in the digital realm. Lurking inside every server farm are rare earth elements lanthanum, neodymium, dysprosium, whose quirky electron configurations make modern computing possible. Hard drive platters rely on alloys containing cobalt and platinum atoms arranged in microscopic magnetic domains, each one a binary switch storing your photos and emails. The screens displaying this content, they're peppered with europium and terbium atoms that glow red and green when zapped with electricity, while indium tin oxide, a transparent mix of metal atoms, forms touchscreen coatings thinner than a soap bubble. Even the humble Wi-Fi router depends on gallium nitride semiconductors, where gallium's 3 outer electrons bond perfectly with nitrogen's 5 to create a material that can oscillate at blistering frequencies. The cloud, that abstract realm where your data lives, is profoundly physical at the atomic level. Superconducting magnets in data center cooling systems use niobium titanium alloys that must be chilled near absolute zero to let electrons flow without resistance. Lithium atoms shuttle back and forth in the backup batteries, keeping servers online during outages, while erbium-doped fiber amplifiers boost optical signals across ocean-spanning cables without converting them to electricity. Each Google search or social media scroll sets off a cascade of atomic interactions, from copper atoms conducting electrons in motherboard, traces to silicon atoms flipping transistor states billions of times per second. What's astonishing is how these atomic technologies scale. A single data center might contain more atoms of rare earth elements than were mined in the entire 19th century, yet they're deployed with such precision that a modern smartphone has more computing power than room-sized mainframes of the 1960s. The Internet's growth mirrors the periodic table's expansion. Just as new elements enabled novel materials, discoveries in atomic behavior like giant magnetoresistance in layered cobalt and copper atoms led to exponential leaps in storage density. Now, quantum computing promises to harness the spooky behavior of electrons existing in multiple states simultaneously, potentially rendering today's encryption obsolete by leveraging atomic properties we're only beginning to understand. This atomic infrastructure has an environmental shadow. Mining rare earths often involves processing hundreds of tons of ore for just a kilogram of usable elements, leaving behind radioactive thorium and uranium byproducts. Recycling these materials is notoriously difficult because the atoms are dispersed in complex alloys. A smartphone might contain 2/3 of the periodic table, blended in ways that make extraction akin to unbaking a cake. Researchers now pursue urban mining, using bacteria to selectively absorb gold atoms from e-waste or designing polymers that pluck specific elements from solution like molecular fishing nets. The future of the Internet may hinge not just on exploiting atomic properties, but on learning to do so sustainably. From the fiber under your street to the satellites overhead, the digital age is less about ones and zeros than about the ceaseless choreography of atoms, their electron shells, magnetic moments, and quantum states all conscripted into serving human connection. The next time you lose yourself in a viral video or send a meme across continents, remember, you're not just using the Internet, you're conducting an atomic orchestra, each note played by elements forged in stellar furnaces and now enlisted in the most ambitious communication project in history. The discovery that atoms could be split didn't just unlock new energy, it revealed humanity's capacity for both creation and destruction on an unprecedented scale. When scientists first harnessed nuclear fission in the 1940s, they stood at an ethical crossroads. The same process that could power cities might also obliterate them. The Manhattan Project's success demonstrated atomic energy's dual nature, ending a world war while ushering in an era where a single bomb could erase millions of lives in seconds. Oppenheimer's famous quote about becoming "death, the destroyer of worlds," wasn't just poetic guilt. It was a sobering recognition that atomic knowledge carries consequences far beyond the laboratory. This tension between progress and peril extends far beyond weapons. Consider medical isotopes like cobalt-60, which can shrink tumors but also cause radiation sickness if mishandled. Or CRISPR gene editing, where scientists manipulate the atomic structure of DNA to cure diseases, yet the same technology might one day engineer designer babies with enhanced traits. Even everyday technologies like smartphones rely on rare earth elements mined in ways that sometimes exploit workers and ravage ecosystems. The atoms themselves are neutral. It's human choices that determine whether they heal or harm. What makes atomic ethics uniquely challenging is the scale of impact coupled with irreversibility. A nuclear accident like Chernobyl renders land uninhabitable for generations, while synthetic biology mistakes could alter ecosystems permanently. The Asilomar Conference in 1975 set early guidelines for genetic research, showing scientists can self-regulate, but as atomic manipulation grows cheaper and more accessible, enforcing ethical standards becomes exponentially harder. A high school student today can order gene editing kits online, and 3D printing could one day decentralize nuclear technology. Yet history offers hopeful models too. The International Atomic Energy Agency's safeguards prevent nuclear materials from being weaponized, while treaties like the New START reduce atomic arsenals. The Human Genome Project dedicated funding to study ethical implications alongside scientific ones. These examples prove that with foresight, humanity can steer atomic knowledge toward collective benefit rather than catastrophe. The key lies in anticipating consequences, not just the immediate applications, but second-order effects decades down the line. Perhaps the most profound ethical question isn't what atoms can do, but who gets to decide. When a breakthrough like nuclear fusion or quantum computing emerges, will it widen inequality or uplift all of society? The answers depend on governance structures we build today, patent laws that balance profit and access, education systems that democratize understanding, and cultural narratives that emphasize stewardship over domination. Atoms don't discriminate. They'll obey whoever wields them, whether that's a corporation, government, or lone innovator. This puts an extraordinary burden on scientists and citizens alike. Researchers must communicate risks transparently without stifling progress, while voters need enough atomic literacy to demand responsible policies. The alternative is a future where technological haves and have-nots are divided by an atomic chasm, some wielding molecular machines and longevity treatments, others left with outdated tools and unchecked pollution. The lesson of atomic science isn't that knowledge is dangerous, it's that wisdom grows more precious with each breakthrough. From Marie Curie's radium experiments to modern nanomedicine, every leap forward demands equal measures of curiosity and caution. The atoms themselves are neither good nor evil, they're mirrors reflecting our collective choices back at us. How we shape them now will determine whether they become the foundation of a golden age or the wreckage of our unmet potential. At the heart of every thought, memory, and flicker of awareness lies a mystery wrapped in atoms. The human brain, with its 86 billion neurons, is often compared to a supercomputer. But unlike silicon chips, our minds don't just process information, they experience it. This distinction has led scientists to an electrifying question. Could the atoms inside our neurons be doing more than just passing chemical signals? Could quantum physics, the rules governing particles at the smallest scales, play a role in consciousness itself? It's a radical idea, one that bridges the gap between the tangible world of atoms and the intangible realm of subjective experience. Take the microtubules, tiny protein structures inside neurons that some researchers believe might harness quantum effects. These hollow tubes made of tubulin proteins aren't just cellular scaffolding. Their precise atomic arrangement could, in theory, allow electrons to exist in superposition, meaning they'd occupy multiple states simultaneously until collapsing into a definite state. This isn't just speculation. Experiments show that microtubules can exhibit vibrational resonances at frequencies that hint at quantum coherence. If true, it would mean the brain isn't just a classical switchboard but a quantum orchestra, with atoms performing symphonies of possibility that somehow translate into conscious choice. Then there's the enigma of anesthesia. Certain gases like xenon or isoflurane can switch off consciousness without disrupting the brain's overall electrical activity. How? One hypothesis suggests these chemicals interfere with quantum vibrations in microtubules, effectively muting the quantum processes that underpin awareness. It's as if consciousness isn't just about neurons firing, but about the way atoms inside those neurons dance, and anesthetics change the music, of course. Critics argue the brain is too warm and wet for delicate quantum states to persist. Quantum effects typically require extreme cold to avoid being drowned out by thermal noise. Yet nature might have found workarounds. Photosynthesis, for example, relies on quantum coherence to transfer energy efficiently in plant cells, even at room temperature. If green leaves can harness quantum tricks, why not gray matter? Some theorists propose that the brain's structured water molecules or magnetic fields could shield quantum processes, creating tiny pockets where atoms defy classical physics. This isn't just about biology, it's about the fabric of reality. If atoms in our brains can generate consciousness, Does that mean consciousness is a fundamental property of the universe, like gravity or electromagnetism? Philosophers call this panpsychism, the idea that even atoms might possess a rudimentary form of experience. It sounds outlandish, but consider, the atoms in your neurons are identical to those in stars or stones. If they can arrange themselves to create joy, grief, or curiosity in you, what else might they be capable of in other configurations? The implications ripple outward. Artificial intelligence built on classical computers might never truly think if consciousness requires quantum atomic interactions. Conversely, if we someday build quantum-aware machines, could they develop subjective experiences? And what does it mean for free will if our decisions emerge from quantum randomness rather than deterministic chemistry? These questions don't just challenge science, they redefine what it means to be human. Yet for all the theories, one haunting truth remains. No one knows how atoms or any physical process gives rise to the smell of rain, the sting of jealousy, or the glow of nostalgia. The hard problem of consciousness, as philosophers call it, may be the ultimate atomic puzzle. We can map neurons, measure quantum vibrations, and simulate brains, but the leap from atoms to awareness still feels like alchemy. Perhaps that's the most humbling lesson. The very atoms that build black holes and galaxies also build the mind that wonders about them, and for now, that wonder remains their greatest mystery. Atoms are the universe's silent architects, tiny, yet mighty enough to build galaxies, life, and technology. They've been here since the beginning, stitching together reality particle by particle, from the fiery chaos of the Big Bang to the delicate dance of DNA inside your cells. Think about that for a second. The same atoms that once burned inside ancient stars now form the very thoughts you're having about them. It's a cosmic full-circle moment where matter becomes aware of itself. But atoms aren't just relics of the past, they're the foundation of the future. Every breakthrough in quantum computing, every leap in medicine, every flicker of light from a distant exoplanet hinges on how these minuscule building blocks behave. The phone in your hand, the air in your lungs, even the warmth of sunlight on your skin, all of it is atoms whispering their secrets to us, waiting for us to listen. And the wildest part, we're only just beginning to understand their full potential. So the next time you take a breath, remember, you're not just filling your lungs with air. You're drawing in fragments of cosmic history, stardust recycled through supernova and oceans and countless lives before yours. Every heartbeat, every blink, every moment of wonder is made possible by atoms collaborating in ways we're still unraveling. Whether they're locked in the heart of a black hole or dancing in the synapses of your brain, they're the unsung heroes of existence quietly holding the universe together, one bond at a time. If this journey through the atomic world sparked your curiosity, don't keep it to yourself. Hit like, subscribe, and let us know in the comments what blew your mind the most. Was it the quantum weirdness, the stellar alchemy, or the sheer improbability that atoms could arrange themselves into something as complex as a human thought? The conversation doesn't end here. After all, every question we ask is just another atom in the ever-expanding universe.